So, welcome back, and today we will discuss the gravitational potential energy and the gravitational potential, which is a very beautiful concept again. We have used the concept of gravitational potential energy and the sister energy, which is the kinetic energy, and the conservation of energy, mechanical energy, etc., etc. So we can say our earlier this thing was, without discussion of the nuances of gravitation, that this potential energy is the energy stored in a body, at its given position. Okay? For example, in this case, the value we took for calculations and for understanding, that was at a height h above the surface of the earth, this value was taken as equal to mgh here. Okay. Now let us see, to discuss the things we do need some of the things. If the position of the particle changes, because there may be several forces acting on the particle, there may be a net force that may also keep on changing, etc. But what will happen is that the position of the particle will change due to the forces acting on the particle. Then we can define that delta potential energy, which means the change in the potential energy is equal to the work done on the body by this net force. So I repeat for you that if the position of the particle changes due to the forces acting on it, the potential energy of the body will equal the work done on the body by the net force. Work done on the body by the net force. Okay, this is a very important aspect. The second thing is that the forces for which this work done, W, is not a function of path. That is, the work done is independent of the path. Whether we, for example, it's easy to understand that if I have body over here and we want to bring this body to this height, it's not necessary that we go along the vertical line. We can go here, stay put for some time, and then we can go to this position. Or I can take this body away from here to here, and then I bring here. The main thing is the initial and the ultimate final position of the body, the two bodies. So you can see that there is an element of path independence, and whenever there is an element of path independence, the forces that we encounter, they are called conservative forces. These forces can be mechanical forces, gravitational forces, any kind of forces, but the main thing is path independence. Okay, now if I say that the force due to gravity is Fg, and this is a conservative force, then we can calculate the potential energy of the system due to the force. So the condition is, one, that any forces that are path independent. For work done is path independent, they are conservative. And gravitation is a conservative force. Like you will find that electrostatic forces are also conservative in nature. So we can calculate the potential energy due to the force. How come? It's very simple. Fg I can write as equal to, we have discussed this, Fg, the force due to gravity, I can write only simply F, doesn't matter. But this is on a mass m close to the surface of the earth is equal to mg. So if, I am just showing to you that there is, this is the surface of the earth, and over and above the surface of the earth, on this line which is the vertical line, we have 2 points P1 and P2 at heights h1 and h2 respectively. The mass is m, and what we are required to do is to lift this body from this position to this position to a height difference of h2 minus h1. Okay, so if P1, from P1 to P2 the body is moved, then I write W1 2, from 1 to 2, the work done. Okay, this is equal to force into displacement in the direction of the force, because you know that this work done is a dot product, force into displacement. So I can write, without discussing the intricacies of that, it's very simple. I just write the force which is equal to mg into displacement which turns out to be equal to h2 minus h1. Okay. Now if we define WH, UH, VH, whatever you like, here I put WH, and it is the potential energy at a height h. Then of course I can write this WH equal to mgh plus W naught. Okay, so W, this will become equal to, from 1 to 2, that is from WH1 to WH2. Okay, so what happens? Now this W naught here, this W naught over here, I take it as a constant. That could be 0, that could be whatever you like. Okay, this value all depends upon you. But I think you will agree with me that 0 is a very appropriate number, or whatever you want to do, but this should remain constant. Okay. Then in that case, what we obtain is W into H2 minus H1, because here I have for W1 H1 here and for W2 H2 here, then I will find that the work done is equal to W into H2 minus H1. So from 1 to 2, and we take this W as the potential energy at a height, the potential energy H2 minus H1. Okay. So we consider that this W0, which was at H is equal to 0, is the potential energy at the surface. And there was a gross mistake. Okay, and that is, I wrote this W12 is equal to W H2 minus H1, but it is WH2 minus WH1. Okay, so it happens. Now, this formula that we obtain, if the value of H is large enough at heights which are not close to the surface of the earth, then this is not valid, as mg is equal to constant is not valid, because the value of g keeps on changing, as we have seen with height. Okay, now let us see. It's very easy. We know that F is equal to capital G mm upon r square, where m is the mass of the earth and r is the distance from the center of the earth. So what we do is that if we lift the particle under consideration from a value r is equal to r1 to another value r is equal to r2, so I can show it to you that this force dr W12 becomes equal to integral r1 to r2 capital G mm upon r square dr. So capital G mm I can take it out, okay, and then this becomes equal to r1 to r2 r raised to the power of minus 2 dr, which we know that according to the formula, okay, this is equal to minus 2 r raised to the power of minus 2 plus 1 divided by minus 2 plus 1. Okay, I am not writing that. It's the same formula. The integration of x to the power of n dx, that is x to the power of n plus 1 divided by n plus 1, provided n plus 1 is not equal to 0. So anyway, so what happens is that the potential energy we could write as WR at the height r is equal to minus capital G mm upon r plus a constant W1. We'll see that this W1 corresponds to the potential energy of the system that we are discussing at an infinite distance away from the surface of Earth. Okay, that value we can take any value, maybe a 0 will do, and maybe normally. So I can write that W12, this potential energy is equal to the potential energy at R1 minus potential energy, I'm sorry, this is R2 minus R1, okay, R2 minus R1, the potential energy at R2 minus the potential energy at R1, okay, just like this equation. Potential energy at the height h2 minus potential energy at the height h1. So there is a correspondence between these two equations. There is a correspondence between these two equations. The only difference is that this equation is valid for heights very close to the surface of the earth, and this is applicable for the heights other than that. Okay, very high values of r. So let me go back to the equation that we derived. W, potential energy at a distance r away from the earth, is equal to minus capital G mm upon r plus W1. Now in this expression, let us put r is equal to infinity. So naturally, when this is divided by infinity, this value becomes equal to 0. And therefore, the W at r is equal to infinity is equal to W1. The constant that we had taken, the constant which we obtained, and by convenience, this constant is taken as equal to 0. That is the potential energy of this, what we are considering is equal to 0 when the distance is infinite. Therefore, I can write WR is equal to just minus GMM upon R. And it gives us the amount of work done to displace a particle from infinity to that point under consideration. So we have this equation, okay, by taking the value of W1 here equal to 0 by convenience. Now, this is whatever we have talked about is about the Earth. In general, in space, if we have two particle masses m1 and m2 held at a distance r apart, how come? We don't care. We don't know and we don't care. But they are situated, and momentarily we think that we have taken a snapshot of it, okay, and therefore they stay where they are in space, in a kind of an isolated system. They are not to be affected by other masses, etc., which are present in space. So in that confined thinking, where I have a mass m1 and another mass m2, whatever their values be, then the gravitational potential energy of this system of two masses, by analogy, by the same way, this gravitational potential energy is a distance r away from each other. This is equal to minus g small m1 m2 upon r upon r, not r square, okay. And of course this value of V, the associated potential energy, gravitational potential energy, is equal to 0 as r tends to infinity, because then this value automatically becomes 0. Now the gravitational potential due to a mass m at a distance r, this is therefore found to be equal to, in the Earth system or any other system, it doesn't matter at all, ur is equal to minus capital G m upon r, which we have to bear in mind that is a scalar. And similarly, this one also, V is equal to minus capital G m1 m2 upon r, is also scalar. So we have talked about the gravitational potential energy and the potential associated with gravitation under a strict condition of the Earth and a mass system, and in general conditions that there are two masses, there is space, they are separated by a distance r. Of course these can vary, all these things. So if m1 varies, m2 varies, and r also varies, you can see that in the system only capital G is there, is constant, and which is a universal gravitational constant. Okay, so we can have a mass, and around that mass there are places where there is a gravitational potential due to that mass. If you put a mass over there, then you will get the gravitational potential energy. Okay. So it has been an interesting talk so far, and next we will talk about the escape velocity. That is a misnomer. Escape velocity is a misnomer, and we'll rather talk about that speed. Okay, not the velocity, but speed, escape speed. And thereafter we go ahead and talk about the satellites close to the surface of Earth, weather monitoring satellites, geostationary satellites, the parking satellites, etc., etc. But one thing I would like to tell you, and introduce to you and think over it, okay? And sometimes the students get confused. That's why I'm talking to you about this, that often the students think that if this is the surface of the Earth, okay, somewhere here, maybe we take it here, okay, and its radius vector is like this, then whether the projectile has to be projected vertically, or we can have an angle at which the projectile has to be projected with what we know as 11.2, which will prove, which will calculate kilometers per hour. No, not per hour, per second. Okay, so this is the speed which is required. What if in a third direction this is projected just horizontally? Okay, well, it's only a simple thing about the conservation of energy, and the energy with which we the centralized projected is one of the same, whatever be the value of the speed. So because this is related to speed, otherwise sometimes what happens is that some students, if this is defined as an angle theta, then what they say is that the speed in the direction of the vertical is equal to that is speed into cos of theta, and then they are at a loss as to what to do. So this bit of falls away from what is exactly the thing takes at us, makes us confused, and need not say that some of you, most of you have been following, they have been not following this, and therefore I insist that while you are going through these lectures, start thinking, start pondering. You have your own beautiful head or your strong shoulders. So may God bless you, and I insist on that, and we meet shortly.